Topic of this lecture is different shades of thixotropy. All right. You must have come across many soft materials in your day-to-day life, which have paste-like consistency. All right. And these paste-like consistency materials, many of them tend to show something called a very unique behavior called thixotropy in them. All right. So this thixotropy manifests itself in various flow behaviors, and those flow behaviors are very intriguing. So these various flow behaviors are being referred to as different shades of this wonderful phenomenon called thixotropy, and that is topic of my presentation today. All right. So I'm going to start my presentation, but before that, let me mention this that I'm giving this online lecture. Many things can happen. I'm using two modes. If electricity goes or if network connection disappears, just bear with me. I'll come back again online and we'll continue the talk. I hope it doesn't happen, but in past sometimes it has indeed happened that things got disrupted. If that happens, bear with us, and I'll come back to you soon on that. Okay. So, well, there is nobody over here who has not used toothpaste. All right. And when you must have taken your undergraduate fluid mechanics course, you were told that toothpaste is a Bingham fluid material. All right. Which simply means that it does not flow until a certain threshold stress is applied to the same. And that gets manifested in its routine behavior. And that is, this is a typical toothpaste carton, and if you put that upside down, nothing comes out. All right. If you press on it, you need to overcome a certain minimum stress in order to make toothpaste flow inside it. And it has been shown using this video. Okay. If something is not supposed to work, it will not work. So I hope that this video works here. Okay. Yeah, it started working. It is writing it on it, but it's not, video is not working. I don't know why. It's no matter. It's just, okay. You can see here that there is no movement under gravity. But when you press upon it, as we usually do every morning, paste starts coming. All right. So this is a typical yield stress behavior that all of us are very well aware of. And we have studied this also very well in our undergraduate days. All right. And there are many textbook problems associated with that in a very fine book by our dear Bird Stewart Lightfoot and the Bird Armstrong Hasager. No, it's Bird Stewart Lightfoot, Transport Phenomena. And so this particular fluid is known as Bingham fluid. All right. And E.C. Bingham is known as father of rheology. Professor Bingham was a professor of chemistry at Lafayette College in New York. Please note that this paper was published in 1916, and chemical engineering as such was not a well-defined discipline back then. And at that time, he actually worked with clay dispersions and observed that a minimum stress needs to be overcome in order to material to flow. And the original paper by Bingham is actually shown over here, and this essentially is that paper. All right. So Bingham introduced the concept of yield stress fluids, and in series of flow experiments in capillaries of different sizes with kaolin water suspension. Now kaolin here is a smectite water loving clay. It's water swelling clay. He worked with kaolin water suspensions, and Bingham observed that pressure needed for flow to take place must exceed a critical value. And Bingham distinguished plastic from viscous flow by requirement for the former that a finite friction needs to be overcome in order for flow to be achieved. All right. And what he called finite friction in his manuscript, we now represented as yield stress, and the corresponding fluids are known as either yield stress fluid or Bingham stress fluid. All right. So typically the Bingham stress fluid, the constitutive equation looks something like this, that viscosity is infinite below the yield stress. When the stress is below the yield stress, viscosity is infinite. So when stress is below the yield stress, there is no flow. Shear rate is identically equal to zero. All right. However, above the yield stress, viscosity follows this relation. All right, which is shown by this straight line over here. Okay. Now I want to bring to your attention a very important aspect over here. You must understand that definition of viscosity according to fluid mechanics is nothing but stress divided by rate of strain. All right. You must keep in mind that it is not the ratio of, it is not the slope of stress strain rate flow curve, but it is the ratio. All right. So when this is the definition of viscosity, even though you see that here a line with constant slope, you must keep in mind that this viscosity is not constant. The viscosity of a material is essentially a line that connects any point on this particular Bingham fluid line to the origin. So as shear rate increases, you can see that slope of this line goes on decreasing, which means that the viscosity of Bingham material also goes on decreasing after it has yielded. All right. So many students have this misconception that beyond yield stress, viscosity of Bingham fluid material remains constant. It is not the case. All right. It remains shear thinning in nature. However, it is weakly shear thinning in nature. Although you say that this mu is constant, this mu is not viscosity. Viscosity is mu plus sigma y by gamma dot. Here sigma y is constant. Gamma dot continuously increases, and therefore you see the viscosity is decreasing as a function of gamma dot. All right, you must keep this in mind. However, if material shows strongly shear thinning behavior, then that is typically modeled by an equation which is known as Herschel-Berkeley constitutive model, which actually is shown over here in this particular expression. All right, and Herschel-Berkeley published this particular beautiful paper. Now people actually use more of a Herschel-Berkeley fluid model rather than Bingham model, and they published it around 100 years back. All right, so you must keep these particular aspects in mind. What is origin of yield stress? A soft material shows yield stress because it possesses an inherent structure, and that structure sustains stress without breaking below a threshold. All right. And of course, for a finite time scale, because when time scales becomes infinite, everything breaks down. But we are not going to go into that particular philosophical limit. Such structures of yield stress fluids are thermodynamically out of equilibrium. All right. Yield stress fluids most likely are not at thermodynamic equilibrium. All right. So if the constituents of the yield stress fluids are athermal in nature, which means that they do not undergo thermal motion or Brownian motion, then the structure is practically dead. And such materials are called quasi-equilibrium materials or yield stress materials. These are quasi-equilibrium yield stress materials. All right. Because although they are not at thermodynamic equilibrium, their structure is dead. So possibility of achieving equilibrium by itself is practically absent. So one can call them as quasi-equilibrium yield stress material. And typical example is highly concentrated dispersion with non-Brownian particles. So this is a typical example of such kind of quasi-equilibrium systems. In most materials, but the constituents are thermal. If the typical particle size of constituents is below 1 micrometer, then they tend to be thermal and they undergo Brownian motion. And when they undergo Brownian motion, the motion occurs in such a way that the structure evolves with time and takes the system closer and closer to the equilibrium state. All right. So let me repeat this. If the constituents of material are thermal, then they continuously undergo the jiggling motion. And this jiggling motion is not just random jiggling motion, but it leads to system travel. Its structure evolves, the system travels in such a way that it goes towards equilibrium, because going towards equilibrium is a natural instinct of a material. The way a hot body kept in cold environment becomes eventually cold, the way that is its natural instinct by virtue of second law of thermodynamics. Any material which is out of thermodynamic equilibrium and has thermal constituents will undergo the jiggling motion in such a fashion that it slowly goes towards the equilibrium state. All right. And such material, that structure that gets built up as a function of time, also breaks down with shear. This particular phenomenon is known as thixotropic phenomenon, and those fluids are called as thixotropic yield stress fluids. All right. So yield stress fluids have two types. One type is these quasi-equilibrium yield stress fluids, where constituents are thermally non-active. But when constituents are thermally active, you get something called thixotropic yield stress fluids. And what those are and how that particular behavior looks like, I'm going to discuss this in the present lecture. All right. However, before going further, there has been a very philosophical debate that is yield stress really a myth, and it doesn't exist at all. All right. And in mid 80s, a very popular paper was written by two giants in rheology, Howard Barnes and Ken Walters, that yield stress is myth. And what they proposed is that the yielding phenomenon is not actually a no flow to strong flow transition, but it is actually a weak flow to strong flow transition. According to them, below yield stress, material flows with extremely high viscosity, but above yield stress, it yields and it starts flowing with lower viscosity. All right. So according to them, yielding is a no flow to strong flow according to classical concept, but according to Ken Walters and Howard Barnes, it is weak flow to strong flow transition. However, people say that the weak flow is so weak that one can actually consider this to be a practically no flow situation. And from engineering applications point of view, one should uphold the yield stress concept. And that is how the yield stress concept actually survived in its initial days. But the present literature very clearly suggests that over practically explorable timescales or for laboratory timescales, the yield stress is not really a myth, but real yield stress does exist. All right. This is what the present understanding is. All right. So with this, let us go to this phenomenon of thixotropy. All right. So what did we say in just a couple of slides back? That for thixotropy to be present, what is essential is continuous these thermal motion of constituents. If constituent motions undergo thermal motion, then only thixotropy can exist. All right. So according to that particular idea, material that demonstrates structural buildup under weak flow, all right, and structural breakdown under strong flow are thixotropic materials. All right. And why structural buildup will occur? Structural buildup will occur because the constituents are undergoing Brownian motion or thermal motion. If that motion is absent, if particles are bigger, if they do not undergo thermal motion or Brownian motion, then there will not be structural buildup and you will have something like a quasi-equilibrium yield stress phenomenon. All right. So whenever the thermal motion is present, you essentially get this structural buildup and you tend to get this thixotropic phenomenon. All right. So this has been explained through this particular schematic, and you can see that these are units which can undergo thermal motion, and with time they simply connect each other. So they have some attractive interactions. These particles have some attractive interactions and they connect each other. Why they connect each other? Because one particle has ability to move and collide with the other particle. And when that happens, then only they can connect with each other. So you can see that a small connection has occurred. And you see this. And with time, this connection becomes broader and eventually it spans the space. It forms a completely percolated network. All right. And this network keeps on building. All right. That is how you get structural buildup. This structural buildup is also known as physical aging. All right. However, if you impose deformation field on top of it, which simply means that you take that particular structure, you don't do anything, then it essentially structure keeps on building. But if you move top plate with respect to the bottom plate, which simply means that you apply shear to it, then structure starts destroying, structure starts breaking down. All right. This reversible phenomenon of structural formation under weak flow or no flow conditions and breakdown of the structure under strong flow conditions is known as thixotropy. All right. So strong flow conditions, structural breakdown, this phenomenon is called a rejuvenation, while no flow or weak flow condition, structural buildup occurs. This phenomenon is called as physical aging. You should keep these particular aspects in mind. All right. What is origin of thixotropy? So, as I mentioned, that presence of material with thermal constituents in a non-equilibrium state is the fundamental origin of thixotropy. All right. So, therefore, the structure of material must evolve with time to lower the free energy. As we all are aware from our thermodynamics principles, that if the temperature and pressure remain constant, Gibbs free energy must continuously decrease to achieve thermodynamic equilibrium. And at the point of thermodynamic equilibrium, Gibbs free energy is the lowest. Keep in mind that macroscopic world that we live in, it's completely dictated by thermodynamics. All right. And second law is that ever powerful law which is responsible for everything that goes on around us. All right. So according to that, under constant temperature and pressure conditions, it is that Gibbs free energy that continuously decreases. And if these constituents are thermal in nature, they essentially, that thermal motion builds structure in such a fashion that free energy decreases. All right. Such lowering of free energy is called as physical aging. And when shear is applied, free energy increases, and we call that regeneration phenomenon. All right. What are the implications of thixotropy? Implications of thixotropy essentially as follows. All right. Assume a material, which is being sheared under stress of this value called, let's call this not sigma 1, let's call this as sigma 0. All right. And because of that sigma 0, a steady state in material has reached whose viscosity is, let's say, eta 0. All right. And its corresponding gamma dot is, let's say, gamma dot 0. All right. Now what we are going to do is that we are going to reduce that particular stress to a lower value. We are going to reduce that stress to a lower value. All right. So we have gone now from 0 to 1. When you reduce the stress, typically what happens is that we observe that when you reduce the stress, all right, structure starts building up, and because of which what you see is, okay, here it seems that I have made a small mistake over here, that I have messed up this particular 1 and 2 symbols. All right. When you reduce the shear, when you reduce the gamma 0 over here, this stress over here, lower stress, structure starts building up, which simply means that gamma dot starts decreasing. All right. So here it should not be 2, but it should be 1. Gamma dot starts decreasing. What happens is that because the structure starts building up, the viscosity starts increasing. So here also it should be 1. All right. However, if I increase the stress, then structure gets destroyed. Okay, all right. Because of that destroyed structure, you essentially see increase in shear rate. All right. And corresponding viscosity can be seen to be decreasing. All right. This is essentially the manifestation of thixotropy. Sorry for the typos over here. So let me repeat this again. When you decrease the stress, structure builds up. All right. And because of buildup in structure, you essentially have reduction in. Did I completely messed it up, by the way, by telling you? Okay, let's repeat this again. Okay. When stress is reduced, okay, structure builds up. Structure buildup means viscosity increase. And increase in viscosity also means that shear rate decrease. All right. So when structure is reduced, we are considering this to be path to be 1. All right. So viscosity increases has to be path of 1, and shear rate decrease has to be path of 1. So actually what I said is right. Okay. On the other hand, when stress is increased, what you say is that viscosity decreases and corresponding shear rate increases. Okay, so there was originally typo, but then what I explained was absolutely right. But a take-home message from this is that before giving a talk, please check whether there is a typo in your presentation or not. All right. So with this, let us move forward. So these are the implications of thixotropy. All right. Okay. So based on that, what we did is that we proposed a model. Okay. Don't go by these complications of this particular model. It's actually quite very straightforward. Let's consider phi to be something like a normalized free energy. All right. Normalized free energy simply means that it's normalized with respect to the equilibrium free energy. And this actually then tends to be the equilibrium state. This tends to be the equilibrium state. All right. And let's imagine that this is the highest free energy state. Highest free energy state. Okay. Again, it's normalized. So we call it phi. All right. So what did we say as aging? Aging is that phenomenon by which free energy continuously decreases as a function of time. All right. So this is the aging phenomenon by which phi decreases from 1 to 0, while under shear free energy increases, which increases from 0 to 1. All right. So what we have done is that we have written a very simple first order equation is that rate of change of free energy is proportional to free energy divided by the time scale, inherent time scale with which structure builds. Okay. And minus of that, because as a function of time, actually free energy decreases. All right. While this free energy increases by application of stress or application of deformation field, so therefore this particular second equation is essentially associated with increase in free energy because of deformation field. This is decrease in free energy because of thermal motion. All right. And what we do is that along with this particular equation, we use this typical Maxwell model as a parameter. Maxwell model is nothing but a spring and dashpot in series. All right. If you solve this particular model, you will get this particular expression. And in this particular expression, we simply relate viscosity and this modulus G, viscosity and this modulus G as a function of phi, where this tau is nothing but equal to viscosity by G. All right. So this is a typical simple rheological model we form. All right. Where something important that we keep over here is this time scale, inherent time scale of a material. We consider it to have a power law dependence on time. All right. So the time at which structure evolves, we consider it to be power law dependent on the real time. So time scale, inherent time scale of a material, you can also call it as a thixotropic time scale of a material. We consider it to be time to the power mu, where this mu is a coefficient which determines the rate of increase in structure. All right. And if this mu is very large, which means that structural formation is very fast, this mu is small, then structure formation is very slow. That is what actually it leads to. All right. And I'm going to show you a very simple prediction of this particular model. And that is, for mu is equal to 1, what we observe is that we see a behavior that looks something like this. So on vertical axis, we plot steady state stress. On horizontal axis, we plot steady state shear rate. And for mu is equal to 1, what we observe is this particular line actually shows a plateau in the limit of small stress. All right. For mu less than 1, we observe monotonic increase. So for this, mu is less than 1. For mu is less than 1. All right. So for mu less than 1, we observe monotonic increase in stress and strain rate. For mu is equal to 1, we see a plateau in the limit of stress versus strain rate. But for mu greater than 1, we observe something called a non-monotonicity in the limit of this steady state stress versus strain rate behavior. All right. And this paper essentially was published around 10 years back in soft matter. But that time, several aspects were not known, which now are actually coming out. And this model tends to predict this behavior very well, actually. So we shall now start looking at what are the implications of this non-monotonicity in the limit of very small shear rate, which this model predicts very well. All right. So for that, what we are going to do is that we are going to use a material which is known to show this thixotropic behavior very well. This is aqueous dispersion of laponite. It has 30 nanometer disc-like particles. These particles have negatively charged face while positively charged edge. So this edge is positively charged. So therefore, when you disperse this in water, as a function of time, this starts building up this beautiful network structure. All right. And a cryo-TEM image is actually shown over here, which very nicely shows a beautiful network-like structure. And just to show how dramatic this particular behavior is, I'll show you this beautiful video. You take water, you add laponite into it. First, salt is added. Salt essentially accelerates the whole behavior. Then laponite is added. When you add laponite, water becomes milky white, but eventually the color, the white color essentially becomes practically transparent. And after good stirring, material becomes so transparent that you'll not be able to figure out difference between clear water and this. And if you keep it for some time, these particles, now keep in mind that these particles are extremely small in amount, okay? They actually form a space spanning network that is so strong that it supports its own weight. All right. So for this case, we use 3.58% laponite. Laponite has density of about 2.5, which simply means that the typical concentration that was used over here in terms of volume fraction is about 1.3, 1.4 volume fraction. All right. So when almost 98 to 99% water is present, just this 1.5 weight percent of volume percent of material, you can see that it forms a beautiful space spanning structure that supports its own weight. And then we take the same material. Here we use lower concentration. So this is actually closer to 1 volume percent. And you can see that this sample actually is a solid. You can very clearly see that when you do it completely upside down, it does not flow. All right. But now you take a rod in it and just stir it. It becomes viscous. All right. And you can very clearly see that when you do upside down, it flows completely. Again, go back to the same position, it again floats. And after some time, it again resolidifies. Okay. So this is the typical thixotropic phenomenon that we are talking about. All right. So let's see what beautiful behaviors that this material shows, which actually can be shown by this laponite dispersion. All right. So what is done in this particular behavior is essentially as follows. All right. What we do is that we put that material in the rheometer and we subject it to different magnitudes of stress. All right. What is plotted on the vertical axis is shear rate induced in the material, and what is plotted on the horizontal axis is time. So what we observe is that when you keep material in between two plates and when you apply shear to it, what we observe is that shear rate does get induced in material, extremely small value of shear rate, but that shear rate continuously goes on decreasing as a function of time. All right. When it is below a certain shear rate, but when you apply that particular stress to be above a certain threshold, then it shows sudden increase in shear rate. All right. So below a threshold of stress, you see material flow ceases. The shear rate gets induced, but that shear rate goes on continuously decreasing. Eventually, it leads to stoppage of flow, while above that particular threshold, it flows and eventually flows with a constant rate. All right. So this behavior is a very peculiar behavior. All right. If you compare this with Bingham flow behavior, then Bingham flow behavior actually showed you that Bingham behavior looked actually something like this. For Bingham material, there was a constant value of stress in the limit of low shear rate, and then it started increasing like this. All right. So when you applied any stress below this, the material did not undergo any deformation, because you can very clearly see that there is no deformation possible below. It only undergoes elastic deformation for classical Bingham. So classical Bingham showed elastic deformation for sigma less than sigma y. However, this material did show finite shear rate below a certain threshold, which eventually leads to stoppage of flow. But above a certain threshold stress, the shear rate continuously kept on increasing, leading to continuous flow. Okay, so this phenomenon is known as viscosity bifurcation, which means that there is a threshold stress below which viscosity tends to infinity, while there is a stress above which viscosity becomes finite. All right. And this particular behavior is one of the implications of thixotropy. It can be very nicely shown to be predicted by this non-monotonic flow curve. All right. Which cannot otherwise be predicted by just this Bingham flow type of constitutive equation. Okay. So this is kind of first manifestation of thixotropy, or first shade of thixotropy, which is viscosity bifurcation. All right. Then this is the Bingham model. All right. And now keep in mind that I'm showing Bingham model by two ways. Okay. So this is one way of representation. This is linear shear rate. This is linear stress. All right. But if I plot log of shear rate, and log of stress, whether on vertical axis you plot log or not, it doesn't really matter, but horizontal axis, if it's log, this phenomenon will look like this. All right. This phenomenon will look like this. Okay. So you should keep that in mind. So we know that when such kind of Bingham material is made flow through a pressure flow, a pipe flow or a slit flow, then what typically happens is that since stress is zero at the midpoint and stress increases in both the directions, the region where stress is below the yield stress, material behaves like a plug. Oh, all right. And in this annular region, it flows. Okay. This is a textbook problem in our Bird Stewart Lightfoot book. All right. This is a textbook problem. And its manifestation in experiment is also actually shown over here. Okay. A beautiful experimental manifestation in a pipe flow or slit flow can be seen over here. All right. However, and why does this occur? This occurs because the stress is non-homogeneous in a pipe flow or a slit flow. Stress continuously changes. Stress is zero at the midpoint and it increases towards the wall. And that's the reason this behavior occurs. All right. However, if we use a scenario where there is a bottom plate and top plate moves, okay, then this situation is constant stress situation. It's a constant stress situation. All right. What is typically observed in this particular case is that if you have sufficiently high shear rate, all right, system shows a completely homogeneous profile. However, if you keep on reducing the shear rate, then the system bifurcates in the two regions. All right. You must keep in mind that this is the flow field. Okay. So this is, you can say that this is the fixed plate. This is the fixed plate where velocity is equal to 0. This is the moving plate where normalized velocity is 1. All right. And fixed plate 0 to normalized velocity 1, there is a homogeneous change. This occurs for high gamma dot. But as you keep on lowering the gamma dot, what happens is that over a region closer to the fixed wall, this is fixed wall, this is moving wall. Okay. Over the region closer to the fixed wall, what you get is no flow at all, but material flows with very high shear rate in this particular wall region. All right. Now, this particular behavior is not be able to shown by our regular constitutive equation, but this is typically shown. This is typically shown by this Bingham plastic. Sorry, what's happening? Okay. This is typically shown by this thixotropic material. And what I'm going to, okay, I'll go back to the. So what happens is that you can very clearly see that this is the typical non-monotonic flow rate, that flow curve that we get. Okay. Let's say that this is a critical gamma dot beyond which stress is proportional to strain rate. Okay. Which means that, please note that fluid mechanics requires that stress to be proportional to strain rate. All right. If there is a negative slope, which means that it is unstable flow. All right. So whenever the applied stress is sufficiently large beyond this gamma dot C, you get homogeneous flow like you saw over here. All right. But when gamma dot is in this region, what do you mean by gamma dot in this region? The top plate velocity divided by h, when h is the distance between two plates, is in this region, you are in an unstable region, which means that the flow field must separate into two parts. A certain part must flow with zero shear rate, while certain part must flow with the highest possible shear rate for which lowest possible shear rate for which the material is stable, which means at this particular shear rate. All right. So this is what is actually observed over here, that material flows with next lowest possible stable shear rate, but for the remaining part of the material, it actually does not flow at all. This aspect is known as shear banding. It occurs in a constant stress profile, which is completely different than what is observed in case of Bingham plastic fluid when you have a stress changing, and Bingham plastic shows this kind of behavior. All right. So one should keep this particular aspect in mind, and this can only be predicted by stress versus gamma dot non-monotonic flow behavior. All right. Now, this material also tends to show time-dependent yield stress. All right. So typically it is observed that yield stress remains constant until a certain period, and then it starts increasing as a function of time. And we recently published a paper. Again, we used the same model that I showed you, and we predicted this particular time-dependent yield stress for this particular material. So this is the third behavior that we observed. Okay. So let me go back. First behavior is viscosity bifurcation. Second behavior is shear banding. Third behavior is time-dependent yield stress. And this time-dependent yield stress can also be predicted by sigma gamma dot non-monotonic flow curve. All right. So this is the third behavior. And you will now ask me a question. Okay. So this is also another behavior that we observed, that you keep material in between two plates and you move top plate with very high shear, and then at some point of time you stop that particular shear and you measure how the stress decays as a function of time. What we observed is that stress first decays and then it starts increasing. All right. We recently published this particular paper in Journal of Rheology. So this stress buildup is fourth type of behavior that we saw. All right. And we also propose that how this stress buildup does not violate second law of thermodynamics. So that paper also appeared a few years back. And you will ask a very natural question now, is that we observe Bingham flow in pipe shows this kind of behavior. All right. Obvious question is that what will happen if you make thixotropic material flow in pipe? All right. And answer to that question is very interesting. So we did these experiments in our lab. We took an injection syringe. This is an in-house capillary rheometer, and we made this particular thixotropic flow in this particular capillary, and we measured the flow rate Q, and we measured the delta P pressure using pressure transducer, and we used the same Laponite dispersion. And what we observed is that depending upon the stress applied, we see different behaviors. Okay. For high stresses, okay, we see a constant normal, constant stress. All right. So this is for 1000 per second, we get this. For 500, we get this value. For 100, we get this value. For 50, we get this value. But for 25, we get continuous oscillations. So somewhere this line is between 25 and 50. All right. And what we observe is that for 25, we get these oscillations. For 5, we get even further oscillations in both stress as well as shear rate, suggesting that this indeed is the region of unstable flow. All right. And such things have great implications because, see, thixotropic materials are very important from industry point of view also. All the pasty materials that we come across in our day-to-day life, let it be toothpaste, let it be pharmaceutical cream, let it be paint, let it be slurries, various kinds of agrochemical and n number of chemical dispersions where solid fluid dispersion is solid and fluid mixture is present. These materials tend to be thixotropic, and one needs to be careful in order to avoid shear banding, in order to avoid viscosity bifurcation, in order to avoid such pressure oscillations in flow field. So from that point of view, these are very important behaviors, and these are different shades of thixotropy. And okay, so this behavior was observed for 3.58% 8 days old sample. This behavior observed for 3.8% 40 days old sample. And you can see that very similar kind of pressure oscillations here also. And that brings me to concluding remarks. Thixotropy is the continuous decrease of apparent viscosity with time under shear and subsequent recovery of viscosity when flow is discontinued. Thixotropic materials tend to show non-monotonic flow curve, which leads to time-dependent yield stress, pressure flow oscillations in pressure flow, stress buildup. What I did not mention here is viscosity bifurcation, shear banding. All right. So these are various shades of thixotropy. And another application I forgot to mention is that thixotropic materials are very predominantly these days used in 3D printing. And therefore, one must be very careful before applying it in 3D printing, as it may lead to various instabilities if you do not take great care in specifying the parameters under which you are using your 3D printer. All right. So with this, I'll conclude my talk, and I'll be happy to take any questions if you have. Thank you.
Thank you, sir. Thank you, sir. So any questions?
Yeah. Hello, Alok this side from IIT Nagpur.
Yeah.
Thank you for this interesting talk, sir.
Can you please put on your video? It's always good to talk to a face rather than for those wherever it's possible. I request you to put on your videos, because then I'll feel like talking to people and not just screen.
Sir, I could have done that, but my MSI laptop is not allowing that at the moment.
Okay, no problem. Wherever
And
it's
I'm
possible,
using
please
Teams,
put on your
yeah.
videos. I don't want to force anybody. Just for all those who are, just put on your videos so that I'll feel like talking to audience rather than just the.
Okay, sir, I have two questions. The first is related to thixotropy nature during welding phenomena, because there are several applications we are using. For example, if we consider the laser welding, yeah, where we have this new technology coming up for the electric motors, and there primarily we are trying to do the laser welding for the hairpin winding. So is there any thixotropic study when the laser, like when the copper melts and that it solidifies, it has some of the impurities in terms of the coating of the copper wire? So that is the first question. Is there any such study involved? And the second question is related to, as you mentioned, the 3D printing. So these days, 3D printing is also being started applicated in the space environment systems, be it the rockets or some of the propulsion systems. So how does the property change when these fluids solidify into at the room temperature, and then further they are exposed to extreme environmental conditions in nature?
Okay, so first things first, regarding the copper welding, I do not know how thixotropy comes in picture. See, you must understand what thixotropy is. Viscosity increase as a function of time under small amount of stress or no stress conditions. So that is one possibility. And second, that is one aspect. And second aspect is that its viscosity should decrease when strong stress is applied. All right, that is second aspect. Okay. So I do not think that copper welding really comes in the domain of such kind of behavior. So unless you tell me exactly what kind of behavior is, I'll not be able to comment on that. That is point one. Point two is what is 3D printing? In 3D printing, you essentially force material out of the orifice of 3D printer or the capillary of 3D printer, and as material comes out, it's in the stationary state, and very quickly it solidifies. It retains its shape while it solidifies, and therefore, as 3D printer progresses printing, you essentially get some kind of a 3D object in your hand. So how quickly material solidifies is essentially essential for 3D printing. So whether you do 3D printing on Earth, whether you do 3D printing in space, it really doesn't matter. The rheological properties of the 3D printing fluid matter.